This is a Tuesday morning, 66 million years ago. The Triceratops is drinking from a river in what will one day be North Dakota. The temperature is 79 degrees Fahrenheit. The sky is clear. There are no storms, no warning signs, no trembling ground. Just a dinosaur and a river and a morning that looks exactly like every other morning for the past 180 million years. Somewhere above the atmosphere, too far away to see, too fast to track, something is coming. 6 miles wide, 40,000 miles per hour. It has been traveling for 4 billion miles to reach this exact point in space. And in exactly 11 minutes and 40 seconds, this river will cease to exist. The Triceratops does not know this. Nothing on Earth does. Not the T-Rex hunting through the tree line half a mile to the north. Not the pterosaurs riding thermals above the inland sea 200 miles to the west. Not the small, warm-blooded mammals trembling in their burrows beneath the roots of ancient ferns. Not a single living thing on this planet. Not one of the estimated 40,000 species alive on this Tuesday morning has any awareness of what is about to happen. Because nothing like this has happened before. Not in the 180 million years that dinosaurs have ruled this world. Not in the 540 million years since complex animal life first emerged from the ancient oceans. What you are about to witness is the most precisely documented catastrophe in the history of this planet. Scientists have spent decades reconstructing it, hour by hour, layer by layer, fossil by fossil, using evidence pulled from the rocks themselves. A fish killed within 2 hours of the impact, its gills still packed with glassy spherules of molten rock that rain from the sky. A layer of iridium, an element rare on Earth but common in asteroids, found in sediment on every single continent on the planet. A crater 110 miles wide and 20 miles deep, buried beneath the limestone of the Yucatan Peninsula, silent for 66 million years. This is not speculation. This is the exact timeline of the last day of the dinosaur age. And it is worse than anything you have imagined. To understand what is about to be lost, you first need to understand the world that is about to end. 66 million years ago, Earth is not the planet you know. It is warmer, wetter, more alive than anything existing today. The average global temperature is 14 degrees Fahrenheit higher than it is right now. There are no polar ice caps. Not at the North Pole, not at the South Pole. Sea levels stand 600 feet higher than they do today, and the map of every continent looks nothing like the one you know. North America is split clean in two by a vast inland sea called the Western Interior Seaway. A warm, shallow body of water stretching 2,000 miles from the Arctic Ocean down to the Gulf of Mexico. Mosasaurs, sea reptiles the length of a school bus, patrol its depths alongside sharks and giant sea turtles. Above the surface, pterosaurs with wingspans of 30 feet ride the thermals over water that has no modern equivalent. This is not a dying world. This is a world at the absolute peak of its biological complexity and diversity. Dinosaurs have ruled this planet for 180 million years, a span so vast it makes the entire history of our own species look like a rounding error. They are not struggling, and they are not in decline. They are thriving, and on this Tuesday morning, there is absolutely no reason to think that will ever change. In the Hell Creek ecosystem, the ancient landscape now fossilized across the Badlands of Montana, North Dakota, South Dakota, and Wyoming. The food chain is dense and stacked from top to bottom. At the very top, Tyrannosaurus rex, 9 tons, 40 feet long, with a bite force of 12,000 pounds per square inch, the most powerful bite of any land animal that has ever lived. Below it, herds of triceratops weighing up to 12 tons each graze across floodplains the size of modern Texas, their great horned skulls lowered to the ancient ferns. Edmontosaurus, a hadrosaur the length of a city bus, migrates in herds of thousands along river corridors stretching for hundreds of miles. Ankylosaurus moves alone through the undergrowth, armored from snout to tail, swinging a club of fused bone dense enough to shatter the leg of any predator on Earth. And beneath all of this, beneath the thunder of the herds and the shadows of the pterosaurs, hiding in burrows and root systems, are the mammals. The largest among them is roughly the size of a modern house cat. They are warm-blooded, fast-breeding, and almost entirely nocturnal. They have lived alongside the dinosaurs for 100 million years by staying invisible, staying quiet, staying out of the way. On this Tuesday morning, not one of them has any idea that within 24 hours, the world will belong to them. Now, the object that is going to end all of this. The asteroid formed 4.5 billion years ago, in the first violent years of the solar system. It is a carbonaceous chondrite, ancient, dark, rich in carbon and trapped water ice. At its widest point, it measures 6 miles across. Set it down in the middle of Los Angeles, and it stretches from the Pacific coastline past the mountains on the other side. For 4.5 billion years, it orbited the Sun in the asteroid belt between Mars and Jupiter, undisturbed. Then, a gravitational nudge from Jupiter pushed it out of its stable orbit, and it began drifting inward. It crossed the orbit of Mars, then the orbit of Earth. On this morning, 66 million years ago, that slow drift finally ends. The asteroid is now traveling at 40,000 miles per hour, 50 times faster than a rifle bullet. It is currently 11 minutes away from the surface of the Earth. And on the banks of a warm river in what will one day be North Dakota, the Triceratops lowers its head and drinks. At 6.3 miles per second, the asteroid enters the upper atmosphere. It does not slow down. The atmosphere, 60 miles thick, the product of 4 billion years of geological and biological history, is crossed in less than 1 second. In that single second, the column of air directly in front of the asteroid is compressed so violently that it superheats to 50,000 degrees Fahrenheit. That is 3 times hotter than the surface of the Sun. The rock itself begins to vaporize before it even touches the ground. Anyone standing within 900 miles of the Yucatan Peninsula at that moment and looking toward the south would have seen a flash of light brighter than 1,000 suns combined. They would have been blinded before the sound reached them. They would have been dead before they understood what they had seen. The asteroid strikes the shallow waters of what is now the Yucatan Peninsula in Mexico, a region of sulfur-rich limestone sitting in just 150 feet of warm, tropical water. This location is catastrophically unlucky. Had the asteroid struck the deep ocean floor, much of its energy would have been absorbed and scattered by miles of water above it. Had it struck a region of hard granite bedrock, far less sulfur would have been vaporized into the atmosphere. Instead, it hits the worst possible target, a thin shelf of sulfur-saturated limestone over shallow water, a chemical accelerant waiting to be ignited. The energy released in the first second of impact is equivalent to 10 billion nuclear warheads of the type dropped on Hiroshima, all detonating simultaneously. A crater begins to form. It will eventually measure 110 miles wide and 20 miles deep. The rock beneath the impact point does not shatter. It behaves like a liquid, flowing outward in a ring of mountains taller than the Himalayas, then collapsing back inward within minutes. A plume of vaporized rock, superheated steam, and pulverized limestone is blasted upward through the atmosphere and into space at velocities exceeding 25,000 miles per hour. Some of it will never come back. Most of it will. The Triceratops by the river in North Dakota, she's still alive. For now. 2 minutes after impact, the seismic wave reaches the edge of the Yucatan Peninsula. It is traveling through solid rock at 4 miles per second. By the time it has spread outward 500 miles from the crater, it has already triggered every major fault line it has crossed. Volcanoes that have been dormant for thousands of years begin to erupt simultaneously across Mexico and Central America. The ground itself, solid, ancient, continent-wide, is moving in waves like the surface of a disturbed lake. 13 minutes after impact, the seismic wave reaches Tanis, North Dakota, 2,000 miles from the impact site. We know this with extraordinary precision because of what Robert De Palma and his team discovered at the Tanis fossil site beginning in 2019. The sediment layers at Tanis record the event in real time, like a geological security camera that has been running for 66 million years. When the seismic wave reaches Tanis, it does something unexpected. The vibrations travel through the bedrock and into the water of a shallow inland bay connected to the western interior seaway. The water begins to slosh violently, like water in a bowl being shaken by an earthquake. This phenomenon is called a seiche, a standing wave created by seismic resonance. The water surges backward, exposing the riverbed. Then it surges forward, fast, carrying sand, gravel, fish, and debris, and buries everything in its path under several feet of sediment in a matter of minutes. Fish are thrown onto land by the hundreds. They are buried alive before they can suffocate, and in their gills, packed in alongside the sediment, are the tiny glass spherules that are already beginning to rain down from the sky. These fish will lie in that position for 66 million years. They will be the most important fossils ever discovered. 2,000 miles to the south, the crater is still forming. The plume of vaporized rock and debris that was blasted into space during the first seconds of impact is now beginning to fall back to Earth. This is not a gentle return. Billions of tons of material, pulverized limestone, vaporized asteroid, molten rock droplets, are re-entering the atmosphere at speeds of several miles per second, all across the planet simultaneously. As each particle re-enters, it superheats the air around it through friction. The sky begins to glow. Not in one place, everywhere. Across North America, across South America, across Europe and Asia and Africa. The upper atmosphere is heating up as if the entire sky has been turned into a broiler. The infrared radiation pouring down from above begins to raise surface temperatures across the planet. In the regions closest to the impact, across the Americas, surface temperatures climb to 500 degrees Fahrenheit within the first hour. This is hot enough to ignite dry vegetation spontaneously. Forests begin to burn, not from a single fire spreading outward, but from thousands of separate ignition points lighting up simultaneously across the landscape. Any animal caught in the open with no shelter above it is killed not by flame, but by radiant heat. The same mechanism as a convection oven. The dinosaurs standing in open grasslands and floodplains die first. The ones sheltering beneath dense forest canopy survive a little longer, until the canopy itself catches fire. The ones in or near water have the best chance of surviving this first wave of killing. Water absorbs heat. The Triceratops by the river, the one we have been watching since the beginning, is still alive. The seismic wave has passed beneath it. The ground has stilled. But the sky to the south is the color of a forge, and the air is growing warmer by the minute. Underground, in burrows insulated by several feet of earth, the small mammals are trembling but alive. They do not understand what is happening above them. They only know that something is deeply, fundamentally wrong. In the ocean, fish and marine reptiles are insulated from the radiant heat by the water above them. But the ocean itself is changing, absorbing CO2 and sulfur compounds that are beginning to dissolve into the surface water, slowly dropping its pH. The acidification of the oceans has begun. It will take thousands of years to fully play out, but it has begun. Above the burning forests, the sky is filling with soot and smoke and sulfur dioxide. The first molecules of the cloud that will eventually block out the sun are rising into the stratosphere. The clock is running, and it will not stop. The impact has displaced an almost incomprehensible volume of water. In the first minutes after the asteroid struck, the shallow sea above the impact site was simply gone. Vaporized, blasted outward, hurled into the atmosphere. What remains is a void, a hole in the ocean 110 miles wide, surrounded by walls of water hundreds of feet tall that are now collapsing inward from every direction. When those walls meet in the middle, they rebound upward into a wave. Then another, then another. The tsunamis spreading outward from the Yucatan Peninsula are unlike anything the modern world has ever produced. In the Gulf of Mexico, the initial wave is estimated to be over 1 mile tall, taller than any mountain in the eastern United States. It reaches the coastlines of what will one day be Texas, Louisiana, Alabama, and Florida within 2 hours, carrying with it a wall of sediment, rock, and debris that geologists can still find today. A distinct layer of impact ejecta buried in the rock record along the entire Gulf Coast. The wave that crosses the Atlantic reaches the shores of what will one day be Morocco and Spain within 12 hours. But the tsunamis are not the most dangerous thing the oceans are producing right now. The asteroid struck a formation of limestone and anhydrite, a sulfur-bearing rock that sat directly beneath the impact site. In the first seconds of impact, an estimated 100 billion tons of sulfur were vaporized and injected directly into the upper atmosphere. This sulfur will combine with water vapor to form sulfuric acid aerosols, tiny droplets suspended in the stratosphere, reflecting sunlight back into space. The effect will be global, and it will last for decades. But that is a problem for later. Right now, 2 hours after impact, the most immediate crisis is fire. Across North America, an estimated 70% of all forests are burning. The sky above the burning continent is no longer blue. It is black, a rolling, churning ceiling of smoke that stretches from horizon to horizon and climbs tens of thousands of feet into the atmosphere. Below it, in the rivers and lakes and coastal waters, the survivors are waiting. They do not know they are the lucky ones. They do not know there are no lucky ones. 1 full day has now passed since the asteroid struck. The fires are still burning. Across North America, South America, Europe, and Asia, the smoke from millions of simultaneous wildfires is rising into the upper atmosphere and spreading. But smoke alone is not what will kill the dinosaurs. The real killer is already in the stratosphere. And it has been there since the first second of impact. The sulfur dioxide injected into the upper atmosphere during the impact is combining with water vapor to form a global veil of sulfuric acid aerosols. These aerosols are extraordinarily efficient at reflecting sunlight. They do not need to be thick to be effective. A layer just a few micrometers deep, spread across the entire stratosphere, is enough to reduce the amount of sunlight reaching the Earth's surface by more than 80%. On the second day after impact, the sky across most of the planet no longer looks like a sky. It looks like a ceiling, a flat, gray, featureless ceiling that lets through only a dim, reddish twilight even at midday. Photosynthesis begins to fail. Not everywhere at once and not immediately, but the trajectory is now fixed. Without sunlight, plants cannot produce energy. Without plants, the herbivores have nothing to eat. Without herbivores, the carnivores have nothing to hunt. The entire food chain, the towering, intricate, 180-million-year-old food chain of the dinosaur world, is beginning to collapse from the bottom up. The large herbivores feel it first. A triceratops needs to consume several hundred pounds of vegetation every single day to sustain its 12-ton body. When the plants begin to die, that food supply begins to disappear, not all at once, but steadily, irreversibly. The T-Rex at the top of the food chain is actually one of the last to feel the pressure. It can go weeks without eating. It can scavenge the carcasses of animals that have already died, but it cannot go indefinitely. Nothing can. 24 hours after the asteroid struck, the temperature across most of the planet is still relatively normal. The full cooling has not yet begun, but the mechanism that will produce it is already in place, spreading silently through the stratosphere at 70 miles per hour, encircling the globe. The Triceratops by the river is still alive. It is standing in shallow water, which shielded it from the worst of the radiant heat. The fires have not yet reached its location. The air is acrid and strange, and the sky has a color it has never had before. But the animal is alive. It will not be alive much longer. 2 years after the asteroid struck, the sun has effectively disappeared. Not literally. It is still there, burning with the same 10,000 degree Fahrenheit intensity it has maintained for 4.5 billion years. But the veil of sulfuric acid aerosols and soot now encircling the planet at stratospheric altitude is blocking more than 80% of its energy from reaching the surface. The global average temperature has dropped by 47 degrees Fahrenheit from its pre-impact baseline. In the interior of continents, far from the moderating influence of the oceans, temperatures have dropped even further, by as much as 65 degrees Fahrenheit. Water that was liquid is now ice. Soil that was warm is now frozen solid. What little vegetation survived the fires and the first weeks of darkness is now dying in the cold. The fern spike, a phenomenon that paleontologists have found in the rock record at dozens of sites around the world, begins here. Ferns are among the hardiest land plants on Earth. Their spores can survive in the soil for years, waiting for conditions to improve. When every other plant has died, the ferns are the first to begin growing back. And for a brief period, they cover the landscape almost exclusively. It is a ghostly, monochrome world, gray sky, gray ash, gray soil, and the pale green of ferns pushing up through the ruins. In the oceans, the crisis is different but equally catastrophic. The surface waters have cooled dramatically, disrupting the thermal currents that drive ocean circulation. The acidification begun in the first hours of impact has continued. The pH of the surface ocean has dropped enough to dissolve the shells of the tiny marine organisms called foraminifera that form the base of the entire ocean food web. When the foraminifera die, everything that depends on them, the fish, the marine reptiles, the great mosasaurs, begins to starve. 75% of all species on Earth will not survive this winter. The dinosaurs, every non-avian species, every lineage that has ruled this planet for 180 million years, are gone. Not instantly, not in a single dramatic moment. They starve, one by one, population by population, across 2 years of cold and darkness. The last T-Rex dies not from violence, but from hunger, alone, in a world that no longer has enough food to sustain anything as large as it. But something survives. The sky is blue again. It has taken 300,000 years. 300,000 years of slow, incremental clearing as the sulfur aerosols settled out of the stratosphere, as the soot was washed from the air by rain, as the carbon cycle slowly, painfully rebalanced itself. But the sky is blue, and the sun is shining on a world that looks almost nothing like the one that existed before the impact. The great inland sea of North America is gone. Sea levels have dropped as the climate cooled and water locked up in new ice sheets at the pole. The vast floodplains where triceratops grazed are now different landscapes, cut by new river systems, covered by new vegetation. The ferns that colonized the post-impact wasteland have given way to flowering plants, which are diversifying rapidly into the ecological niches left empty by the extinction. There are no dinosaurs, not one. For the first time in 180 million years, the land belongs to something else. The mammals have emerged from their burrows into a world without predators larger than themselves. They are still small, but they are breeding fast, diversifying fast, filling every available role in the new ecosystem with a speed that the fossil record describes as almost explosive. Within 10 million years, every major lineage of modern mammals will have appeared. Whales will return to the sea. Bats will take to the air. Primates will begin climbing through the trees of what will one day be called Africa. And 66 million years from this moment, give or take, one particular lineage of those primates will develop the capacity to look at a rock, read its layers, and reconstruct the exact sequence of events that made their existence possible. That is not a metaphor. The carbon in your body was forged in stars that died before the sun existed. The calcium in your bones was processed through the bodies of marine organisms that lived and died in oceans that no longer exist. And the reason you are here at all, the reason any mammal is here, is that on a Tuesday morning, 66 million years ago, a rock 6 miles wide arrived from the outer solar system and ended the world. The crater is still there, buried under limestone, silent. The fish at Tanis are still there, preserved in the sediment of that terrible Tuesday morning. And the story they tell of catastrophe and survival, of an ending that was also a beginning, is the story of every living thing on Earth today, including you. In 2022, NASA's DART spacecraft deliberately slammed into an asteroid called Dimorphos at 14,000 miles per hour and successfully changed its orbit. It was the first time in history that a human civilization had demonstrated the ability to deflect a space rock. The dinosaurs had no such option. They had no warning, no technology, no awareness of what was coming. We do. Right now, NASA's Planetary Defense Coordination Office is tracking more than 2,000 near-Earth objects classified as potentially hazardous. Rocks large enough to cause regional or global catastrophe if they were to strike. None of them are on a confirmed collision course with Earth. But the solar system is a dynamic place, and the gravitational interactions that sent the Chicxulub impactor on its path 66 million years ago are still happening today. The question is not whether another large asteroid will eventually cross paths with Earth. The question is whether we will see it coming far enough in advance to do something about it. The second thing the Chicxulub impact teaches us is about the speed of ecological collapse. The food chain that had sustained itself for 180 million years began to fail within days of the impact. Not because the asteroid destroyed it directly, but because it disrupted the energy source that held it together. Sunlight. Climate scientists studying the impact winter of 66 million years ago use exactly the same physical models to simulate what a large-scale nuclear exchange would do to Earth's climate today. The mechanisms are identical. Particulate matter in the upper atmosphere, reduced sunlight, failed harvests, cascading food chain collapse. The timescales are different. The physics are the same. And the third thing, perhaps the most important thing, is this. The animals that survived the impact were not the strongest. They were not the largest. They were not the most dominant. They were the ones that could adapt fastest to a world that had changed overnight. Small body size, flexible diet, the ability to survive on very little, the ability to reproduce quickly and generate variation in a population under pressure. These are the traits that carried life through the darkness of 66 million years ago. They are the same traits that have allowed every subsequent lineage, including ours, to persist through the smaller catastrophes that have followed. Resilience is not about being the biggest thing in the room. The fossil record has proven that definitively many times over. We began this story on a Tuesday morning, a triceratops at a river, a clear sky, a world that had existed unchanged in its fundamental structure for longer than the human mind can meaningfully grasp. That world is gone. Every animal that walked those floodplains, every creature that swam that inland sea, every pterosaur that rode those thermals, gone within 2 years of a single Tuesday morning. But here is what did not go. The river is still there. Different river, same watershed. Water that has been cycling through the atmosphere and the ground and the ocean for 4.5 billion years. The sky is still there, still blue, still driven by the same atmospheric chemistry that has been running since long before the first dinosaur drew breath. And the life is still there, diminished, transformed, unrecognizable from what it was, but still here, still finding a way. Robert De Palma held that fish fossil in his hands in 2019 and understood, in the most visceral possible way, what it meant. A creature that died on the worst day in the history of vertebrate life on Earth, and whose death 66 million years later was helping the descendants of the survivors understand exactly what had happened. There is something in that which goes beyond science. The asteroid did not have the last word. Life did. It always does.